Good afternoon, everyone. It is wonderful to see you all here, and thank you for the opportunity to co-host this amazing event. My name is Ben Shoebridge, and I'm Deputy Head Boy at Caldy Grange Grammar School. For the last 13 years, I have been involved in a variety of eco-projects.
Good afternoon, everyone. My name is Gabriella Hyde. I am a Year 10 pupil at St John Pleasanton Catholic College and the Vice Chair of the Worldwide Eco Council.
We are excited to be here today at Eureka, where we will be speaking with researchers based in Antarctica on the work they are doing and its relation to climate change. We will also have the opportunity to hear from the people responsible for engineering and building the ship these researchers are on.
Today we'll be learning from BAS researchers exactly what research they get up to, how this is supporting tackling climate change, and what life is like for researchers out in the field.
The researchers are currently in Antarctica, living and working on the research vessel, the RRS Sir David Attenborough.
The ship was built by the Birkenhead-based Cammell Lairds only a couple miles from where we are sitting right now. John Drummond, the project director for construction of the ship, will now introduce it and take us on a virtual tour.
Good afternoon, everyone. Firstly, it's a pleasure to be invited here to speak about the vessel that spent 6 years of my life building from the first plate to what you see now. So the first sort of picture that you can see there is of the heli deck. So the ship is equipped to carry 2 Eurostar helicopters as and when required. The helicopters are mainly used for emergency rescue and also for transporting any sort of small supplies onto the ice. So the next picture there is what's called the integrated bridge. This is where the captain and the navigator will sit and they'll steer the ship. As technology has moved, the ship is steered from like a console, from like a racing car seat, and the captain can control the seat, can control the ship with just one hand to be able to turn the ship to port, which is to the left, or to the starboard, which is to the right. He's able to keep the ship in position. One of the most important aspects of the vessel when it's doing its science experiments is that the ship needs to be able to stay in the same position, and that's called dynamic positioning. So the ship can go to a satellite and it will record the data on the bridge, and with the thrusters that he's operating, he can keep the ship steady in gale force winds 5 or 6, and that's 30 knot winds. So it's a really very strong vessel. As you move down now, these are the living facilities and the eating areas, the galley. It's a bit of a difference between, it's not cruise ship standard, but they certainly get well looked after on the vessel. So this is like the lounge. This is where they can relax. Come in. It's got a lovely setting. So obviously during their experiments, they do need to have time to relax. So these are a 2-berth, classed as a scientific cabin. So this is where they can relax. There's TV, they have fridges. They are very, very comfortable. So these are now down into the centre of the ship, and these are where the scientists will do their work. Obviously, when you speak to the scientists a bit later on, they'll be able to tell you what they do. But these have lots of data. So some of the experiments that they've done, they plan to do over 2 years, so they have 6 months down in Antarctica just to carry out their specific areas, whatever the scientists deal in. So one of the main aspects of the vessel is what's called a moon pool. As you can see, the yellow line there, it seems a bit odd, but this is like a 4-metre square section that goes right through the centre of the ship. So if you were to stand on there and look inside the moon pool, you'd see the ocean. And people get always a bit weary that there's a hole in the middle of the ship. But it won't sink. So this is where they do their experiments. So this is on the aft deck. So this is where they do their seismic experiments, where they drop sonars and buoys over the back of the vessel, and the ship will go at whatever speed, 13 knots, and they'll take samples of the ocean And this is where a lot of cabins come on board for specific science experiments. So the ship is it's like a diesel electric car. So there's four big generators that are in the engine room, and these generators power alternators. The alternators then send the electrical power to switchboards, and then the switchboards distribute the electrical power to electric motors, and the vessel is propelled by propellers via electric motors. So it's gone away from a standard ship where you have an engine, a gearbox and a tail shaft. So this is like a hybrid electric vessel. So one of the other main aspects of the vessel is its exploration and its winch room. So this is a fully automated winch area, and this have various type of winches. So some of these winches here have got up to 10,000 meters of wire on them. So the ship is able to trawl wires over the shelf in the Atlantic up to 8,000 meters to get whatever it needs from the seabed. So this is the leading ship in the world of this type of activity. I was lucky enough when these winches were being built. I was over in Vietnam where the winches were built, and we called factory acceptance tested them. So it's a great innovative idea that went into this vessel during the build. All right, thank you.
Thank you very much, John. That was extremely interesting, and it was fascinating to see how versatile the ship is. Now we've virtually explored the ship and have a sense of what it looks like. I think it's the moment we've all been waiting for. Kindly giving up their time to talk to us today, live from Antarctica. Please give a round of applause to Sophie Fielding, Emily Rowlands and Flo Atherden. Now the first questions are from Birkenhead Park High. If you'd like to come up and ask your questions.
How does your research benefit the wider world?
So I'll take this. I'm Flo. So the poles are really important for regulating our climate, and they're also really important for driving global ocean circulation. So it's in these cold environments that we get dense, very salty water that's really cold. And because it's so dense, it sinks into the deep ocean. And it's this process of sinking that drives global ocean circulation, and that impacts our climate and our weather patterns. It's why the UK is a relatively pleasant place to live, weather-wise. And so the polar oceans are also really important for taking CO2 from the atmosphere and storing it in the deep ocean. So it helps us mitigate some of the CO2 that's in the atmosphere as well. So it's really important to study those environments and understand the processes in order for us to be able to make decisions about climate change. So personally, I was at COP28 this year, so I was helping explain some of the science to policymakers and help them advocate for stronger climate decisions.
And our next question.
What is the most interesting thing you've found out recently?
I can take this one. So I'm Emily. I work on plastic pollution. Plastic pollution can be anything from your larger macroplastics, so plastic bottles, for instance, or lost fishing nets in the ocean. But plastics also go down to the very small size. So you have microplastics, which can be around the grain size of a grain of sand, but also nanoplastics. And these can be just a fraction of a grain of sand. So very, very small. You need a very powerful microscope to see these small plastics. But we do know that they are in the ocean. And so what my work was looking at is how these very small plastics can impact Antarctic krill. So krill are super important for the Antarctic marine environment. They're huge swarms of krill which attract whales to the area. They basically support the entire marine food web. And so we were looking at what impact these small plastics have. And what we actually found is that krill eggs, so at the very, very early stages of their life, these krill embryos, they can take in small plastics. And I thought that was a particularly interesting finding, because it shows that it's not just these bigger plastics that we need to think about. It's also plastics that we can't necessarily see, but we know are there.
Is this job role one that will withstand the test of time, or will it likely be replaced by AI?
So I'm going to take this. So hi, I'm Sophie, and I would say actually that AI and robots are really augmenting our science rather than replacing us. So they're making us do it differently, but they're also giving us new opportunities. So for example, I use autonomous vehicles, some that kind of go underneath the water and rise up and down, or some that are at the surface. They don't have people on board. And so essentially we can go and send them to places that we ourselves wouldn't want to go. So either the Antarctic in winter where the weather's horrible and it's not very pleasant to work, or maybe up against ice shelves where actually you have to worry about ice calving and that humans are at risk. So that's one area that I think we're really augmenting our science by having that technology available to us.
Okay, thank you. And can we have St John Pleasanton, please?
Thank you for the question.
At what level was CO2 healthiest for our planet, and when was this?
So the global levels of CO2 in the atmosphere are constantly in flux, and they've been in flux since the beginning of when Earth was formed. And there are lots of natural processes that can increase it or decrease it. The issue with net zero and with climate change is that we need to focus on the CO2 that is being forced into the atmosphere by human activity. So that's the important part of it. And so the baseline that we use generally for that is pre-industrial levels. So this is before the Industrial Revolution, before the invention of the steam engine, that kind of thing. So in all of the international climate change agreements, they refer to pre-industrial levels, but actually this isn't strongly legally defined as of yet. So there's no strong legal definition for what time period that actually means. From the science perspective, the scientists who advise these governments tend to use temperature as a measure. And they take a global average temperature from 1850 to 1900, and they use that as the baseline. Yeah.
Thank you. Thank you.
Can the ratio of all gases be tracked through history by looking at ice cores, or is there some other way of getting this information?
So we absolutely use ice cores to kind of trace our carbon dioxide history. And in fact, many scientists, many figures show that. But in addition to that, we can actually use deep sea sediment cores, and they're an important source of proxy material that can go back tens of millions of years. And essentially what happens is as carbon dioxide goes into the oceans, it changes the pH of the water, it increases the acidity, and that actually influences the isotopes that are found in the fossils and other carbonate chemistry, like foraminifera fossils and other kind of planktonic species. And actually really exciting. I mean, I know you're at Liverpool, you've got Cammell Laird around that built the ship that we're standing on at the moment, but we have new technology on this ship that enables us to collect a core that's 40 meters long from the seabed, and that can actually go back in our past climate about 3 million years. So those are the kind of samples that scientists coming on this ship will take, and that's the kind of analysis that they will look at.
If the ice caps all melted, does this mean that the Arctic could have plants growing? And just so, what type of ecosystem would it become?
Thank you. Yeah, so absolutely, vegetation would grow. So essentially, if the ice melts, you're going to have some kind of land mass that's there. Airborne seeds will spawn vegetation on there. They could also be transported by ocean drifting material. And actually, a good analogy for this is actually what happened in the island of Surtsey. If you look it up, it was off Iceland. And it was an island that was only created in about 1960s, mid-60s. And it emerged, and scientists have been using it as a test case for kind of colonization of what happens. So you'll start off, you'll get some kind of pioneering species like mosses and lichens. And then after that, animals will arrive, and actually they will add nutrients to the soil living on there by defecating on the island, etc. You've got guano, things like that. Then you'll get seals. And basically, as they kind of make that environment more nutrient rich, you're going to get more and more species arriving through the kind of airborne side of things, the seaborne side of things. The only bit I was talking to some of our paleoclimatologists about this, and they said, you know, one of the things, we're still in the Antarctic, it's really, really windy. So eventually when you start to get those kind of plants arriving, they're really hardy plants. They don't grow, you know, you don't get tall trees in the Antarctic. You get those kind of like tall bushes that are withstanding the kind of winds that are sweeping down on them.
What do you miss more? What don't you miss about your family and friends?
What do you miss? What do you miss most apart from family and friends?
Thank you. Yeah, as well as family and friends, which is sort of the most difficult part of being away at the sea, I think. Personally, I love the outdoors. I love to hike. I do a lot of paddleboarding when I'm at home, and so being on the ship, it can sometimes feel confined in a sense that you can't do those activities. On the SDA, we're really lucky actually because we have the heli deck, which is a big outdoor space. We can go and do sort of lots of walking in laps around the heli deck, which is what we were doing yesterday. Actually, walked 5 kilometers around the heli deck, and yeah, as well as sort of, you know, doing those laps, we can see the wildlife that's around as well. So that's a really nice substitute, I think, for what I actually miss, which is mainly the hiking.
Thank you very much. And next up, we've got the Caldy questions, please.
With the increased presence of humans in the Antarctic region, is the British Antarctic Survey using any sustainable methods of power and infrastructure to support their work?
So absolutely, you know, we have net zero kind of carbon aspirations as much as everybody else, and especially, you know, as an environmental research institute. So for example, we already have solar panels at many of our stations, but actually, of course, in the winter, some of them are so far south that they have a continuous nighttime called polar night. So solar panels aren't that useful at those kind of times. So in addition to solar panels, we have wind turbines down there. They're a lot better. It can be very windy down here. So that works well. And for example, Halley, our station that's on the ice shelf in the Wirral Sea, they have a wind turbine, and that actually keeps sensors monitoring the environment all through the winter autonomously, so remotely. We don't actually have any people there anymore.
How is your work benefiting net zero's targets?
So because the poles are so important for regulating our climate, it's really important that we understand the processes that are taking place here, and also that we understand how they're changing and how fast they're changing. So a lot of climate change that's happening at the poles is happening a lot faster than we had initially predicted. So the Arctic is warming 3 to 4 times faster than the global average temperature, and the Antarctic is warming about twice as fast than the global average temperature. So when we're at these big global climate meetings and people are talking about accepting a 1.5 or a 2 degree temperature change, in the Arctic, a 2 degree temperature change could be as much as 8 degrees, for example. And if we're thinking about the melting point of ice, that's a massive difference. And at 2 degrees, we start to see processes change to a point where it's really hard to get an environment back that we would recognize. There's no country on Earth that would not be affected by these changes at the poles. It's incredibly serious. And so what we can do as scientists is we can model what are the differences between 1.5, 1.6, 1.7, 1.8, all the way to 2 degrees. And what that science is showing is that those 1/10 of a degrees make a massive difference to how much damage we cause. And because we have this information, we can tell policymakers, and then they're armed with all this information so that they can negotiate for much stronger climate commitments.
Thank you.
Okay, can we have Claire out, please?
Is there a change in size and distribution of the icebergs across the Antarctic?
So That is a difficult question to answer. So there are places in the Antarctic that are warming up, and there are places that are cooling down. And so, you know, if we take the most recent iceberg, for example, that we've been studying in the British Antarctic Survey, I don't know if you saw it on the news, for example, A23A, and that iceberg actually got released from the shelf around 40 years ago. But then it grounded and it sat on the shelf, and it sat there for the last 40 years without moving because it was just too big and too deep and too much of it to move. And so it was only this year finally last year that it started to move across the Antarctic, started to make its way north. So you're kind of saying, is there a change? I mean, when did that change happen? Did it happen, was that iceberg created 40 years ago, or was it created as it got released kind of finally from the shelf this year? So I think we just know that we know that the processes of the changing world are increasing the ice melt underneath the glaciers, and the icebergs are being released.
What we do know is that the nature of the sea ice is changing. So instead of having sea ice that stays for multiple years, we get a lot more sea ice that's only staying for 1 year. So in that sense, we have a lot more less permanent sea ice, and that can change where the sea ice is flowing, how deep it is. And in the Antarctic, there's implications for the wildlife. But up in the Arctic, where people live, this has massive implications for Inuit people in terms of how they get across their country and how they get across their land. So there are big changes to the sea ice taking place.
And what signs of global warming can be seen?
So as the oldest person here, I suppose I'll say, so I've been very, very fortunate to be with BAS for about 20 years. And in that time, I've actually visited the subantarctic island of South Georgia annually. And what's really interesting about that is actually there are glaciers all over South Georgia, all around it. And I can visually see beaches that before were covered by a glacier that I can now walk down because those glaciers have retreated. On top of that, we have our more scientific, if you like, devices where we're monitoring the air temperature, we're monitoring the ocean temperatures, and we've seen an increase in the air temperature over the last 30 years around South Georgia. So, I mean, air temperature is not something you can see, but definitely walking around the glaciers and actually seeing beaches that were originally isolated, two different beaches separated by a glacier, and that they are now one beach.
And are the skies clear at night? Can you see the constellations more clearly?
So when we work in these environments on ship, we tend to be here in summer because the weather's a lot nicer, and that's when a lot of the exciting biology is taking place. And because we're at the very top of the... Oh, sorry. I'm just going to...
Right. They'll do it. Sorry, okay. Just an alarm in the ship.
Just an alarm going off. So because we're working right at the top of the globe, and we're at these really, really high latitudes, the sun in the summer doesn't actually dip below the horizon because we're so high up. And so it means that we get 24 hours daylight. So far when I've been on ship, every time I've got the graveyard shift, I've had the night shift, but it's never actually been dark. So I haven't seen any constellations when I've been on ship. But I have lived in the Arctic, and I've lived there in the winter, and during that time it's 24 hours darkness. So in that environment, I saw stars and constellations and aurora borealis at 1 p.m, all throughout the day, just constant darkness.
Okay, and our next questions are from Woodchurch High.
How do you dispose of waste?
So really interesting question. So we don't leave any waste in the Antarctic. That's one of the kind of environmental policies. So we bring it all back. And essentially that means that we, at the end of the season, the Sir David Attenborough actually has holds full of waste, all sorted into different recycling kind of things. Wherever we can do, we'll recycle as much as we can. And seriously, I don't think you've seen bins like it. I think we've got about 8 different bins on the ship, right? So, you know, you've got your food, you've got your cardboard, you've got your plastic, you've got your batteries, your metal cans, your glasses, all of that stuff. So there's a very clear waste policy. But what is interesting is you know, not only do we have everything for 6 months on the ship, but we actually have everything for people living for a year on the stations as well. It all gets sorted into containers, they get put on the vessel. And to be honest, we actually bring a lot of it all the way back to the UK. And the policy for doing that is to ensure that it is actually dealt with correctly. You know, the UK has some very good policies around, you know, waste management, making sure it just doesn't go into landfill, you know, that we're trying to kind of reach our recycling kind of levels. So yeah, actually we don't dispose of it down here, we bring it all back.
What food do you eat?
So we're very lucky on the ship, actually. There's a great variety of food, very good food. I think one thing to note would be, as time goes on, you know, we're at sea for quite a long time, sometimes, you know, 2 or 3 months, and there's only so long that you can keep vegetables and fruit fresh for. So towards the end of the cruise, this becomes something that's you know, something that we all miss. And when we get back to shore, it's certainly the first thing that we're looking for is some fresh fruits and vegetables. But I think
bit of iron brew, isn't it?
But we're very lucky in the fact we also have a permanent endless supply of ice cream on the ship, so it's very good.
What would you say to someone that didn't believe in climate change and global warming?
So we as scientists, we don't have an agenda. Our job is to observe the environment, to figure out what processes are taking place, and then to report back what we have found. And what we have found with climate change is that 1, climate change is happening, and 2, it is happening due to human influence. So it is human-caused climate change. And we have an overwhelming consensus of scientists that agree on this. And actually, that's actually very rare to have so many scientists agree so strongly on one particular subject. What I would say to someone who is skeptical about it, it's often about having a conversation. It's better to have that conversation face to face and to come from a place of respect for each other, and try really hard just to try and answer people's questions from a non-judgmental place. This is much better done face to face rather than like behind a keyboard at like 2 a.m. And you might not be able to convince people straight away, but you might be able to plant a seed. And it's much easier for people if they put a face and a person to these very large and heavy subjects.
Okay, and could we have Aldershot, please?
As well as scientists, what other professionals are involved in making an Antarctic trip happen?
So we're very, you know, we're talking to you today as scientists. That's very true, but we wouldn't be here without a plethora of kind of support people. So we could start with the ship. We're on a ship, right? So anybody in the maritime world, right from engineers, kind of navigators. We absolutely fundamentally rely on deck people who are deploying our gear over the side, recovering it, chefs, pursers, our logistics staff who get us here. I mean, I kind of sound like I'm accepting an award and thanking all of the cast, right? Because essentially, you know, all of our science isn't delivered unless we rely on these support people. Once you start getting to the stations, we need carpenters, we need plant specialists, plant materials. We have people whose role is actually just to drive a JCB and move snow out of the way so that the planes can get in, so that people can move around. We have field assistants, so we need people who are kind of outdoor people, mountaineering people, climbers, etc., who can actually look after us to make sure that we don't put ourselves in danger. So they're there to kind of manage the expeditions. We have pilots. I mean, the list is quite endless. I think, you know, there are an awful lot of careers that you can take that will bring you into the Antarctic environment. Electricians, and at the moment there's a massive amount of construction that's happening at Rothera, so we're rebuilding our station there. So essentially there's 50 plus construction staff who are on the island there. So they're fabricating new buildings for us, installing new solar power, new wiring, you know, everything. So I think sometimes I might throw the challenge back and say, would you like to think of a career that wouldn't take you to the Antarctic? And I think that, you know, there are some, but it's not that many anymore.
Thank you.
What advice would you give to a young person who wants a science career?
That's a really good question. I think, you know, these core science subjects are very important. So if you think about, you know, the type of work that we do, is you just need to understand the biology, so the animals, but also you need to understand the physical oceanography, you need to understand the chemistry in the water. And I think, you know, focusing on these fundamental science subjects will give you that background knowledge you need to go further into more specialized scientific subjects in the future. You know, also volunteering is great if there's anything that you can get involved with in the sort of science that you're interested in. It can build a really good picture for you of what the day-to-day life is like in that scientific area, and whether that's something that you'd be interested in pursuing. And also the internet is an endless resource, right? So we have the International Polar Foundation, for instance. If you were interested in polar science, there's a huge range of online resources, you know, going into very sort of different areas of the Antarctic marine system, and that's a really good place to get information as well.
All right, and last but certainly no means least, could we have Meadowside, please?
How can schools get more involved in your work?
We really appreciate these sorts of events. I grew up in Scarsdale, so not actually so far from Liverpool. It's really nice to speak to local schools and sort of give an overview of the work we're doing and speak to the next generation of scientists coming through. We also work with the UK Polar Network, so this is a voluntary group of early career researchers, and they're really trying to cascade you know, scientific information about Antarctica to schools. So we have an Antarctic flag system, and this is celebrating the Antarctic Treaty, which is where it was sort of agreed to protect Antarctica and to use it for scientific discoveries. So to sort of educate people about this, you can design flags, which we bring down on the ships with us and cascade to research bases. So we take pictures with these flags in various areas with the penguins, with the seals, and then send those pictures back to you. So you can sort of create something that comes to Antarctica and then you receive it back afterwards. We've also got lots of sort of crowdsourcing campaigns. So particular favorite that I like is you can become a walrus detective. And what this is a satellite imagery, and you're looking through these images to try and find the walrus. So scientists at the British Antarctica are trying to understand what impact the changing climate is having on walrus. It's something you can do as a school. You can create an overall account, and it's a really nice way to get the whole class involved. It's almost like a game. You look through these images and trying to find out where the walrus are. So there's also different options with penguins as well, a whole range of different citizen science activities that you can get involved in.
Okay, thank you.
What is your percentage rate of ice melt year upon year?
So when we look at climate change measurements, these environments are very variable. And so we try in general to look across multiple years rather than just looking year on year. So we try and get data that covers decades. If we think about the Arctic sea ice extent, decade on decade, it loses about 12% of the Arctic sea ice extent every decade. There are some exceptions to this though. So sometimes we look at a particular year because it's particularly outstanding. In 2023, in the Antarctic sea ice, we saw a massive drop in the extent of the Antarctic sea ice, and it was well out within the range we would predict to be natural variability. So what we saw was a 16% reduction in 1 year from the extent of the Antarctic sea ice extent. And just to give you some context for how much ice that is, it's a little bit bigger than Brazil and a little bit smaller than China. That's how much ice suddenly went in 2023.
Thank you.
Okay, so thank you very much, Sophie, Flo and Emily. They were brilliant answers. And thank you to everyone here for your equally impressive questions. Now, I think we're going to cut the link shortly, but can we all give them a massive round of applause, please?
Thanks very much for all the really interesting questions. We really enjoyed it. Thank you.
Thank you very much, and good luck on your next few weeks, months on board.
Thank you.
Okay, so now we've heard from the researchers using the ship. How about we hear from one of the people responsible for its construction? Please welcome once again Project Director for the construction of the ship, John Drummond.
Right. Well, that was really interesting to actually see what the ship's doing. You know, we let the ship go about 2 years ago, so to actually see what it's doing, it was personally, it was really interesting for me, and it's good to see so many young people asking really some good questions. So I'll try and give you a flavour for how we built the ship. So some of the dimensions of the ship: 128 metres long. It's where it says breadth and moulded, that means the width of the ship is 24 metres. When it's got the draft is the amount of steel that sits below the water. So for the likes of the Sir David Attenborough, it's 7 metres of steel that's under the sea. From like a steel weight perspective, they call what's called a dead weight. And even though that figure is 4,475, the actual steel weight involved in the ship was around about 7,000 tonnes. So the ship was designed as an exploration vessel, what you spoke to the scientists about, a cargo handling, because you have to take lots of cargo down to the Antarctica. So the cargo areas is 2,200 metres square, and also we took what was called bulk abtar. Now this is aviation fuel, because there's helicopters that run from down in the Antarctica. So the ship at the back end, which is called the aft end, has AVCAT tanks in. So that's full of aviation fuel that is then decanted to the shore. So the operations of the ship that we've been through there, deployment and recovery of science packages, 9,000 metre depth, what we spoke about, the winches, the seismic survey, and when it says VERTRA operations, that's to do with helicopters. And the advanced ROV, they're remote operated vehicles, and that's what they put through the moon pool so that they can do their experiments under the water. So the picture there you can see is in the starboard engine room. So because of the nature of the vessel, it goes such a long distance, it has 2 engine rooms, and each engine room does exactly the same task. So in each engine room there was a 9-cylinder and a 6-cylinder generator, and it was so that if ever there was a damage in one engine room, the other engine room could supply the same amount of power to keep the ship safe. So the maximum speed was 17.5 knots, and its cruising range of 30 knots was 19,000 nautical miles. So to keep all that power, they say there was 2 Bergen 9-cylinder generators, there's 2 main motors, and then in case of failure of generators, you have what's called a harbour generator, you have an emergency generator, and also there's certain battery systems on board. Because the vessel is working in such remote areas, it needs to make sure it's got lots of redundancy and a lot of backup power to keep it safe. So, how would you go about building a ship? So this is in a test tank here that is frozen. So we went over to Germany in Hamburg and we built a model which is the 20th of the size, the same shape of the hull form there. So we froze the test tank overnight, and what it does, the test tank had an inch of ice in it, and that replicated that the vessel could break a metre thick ice when it's in the Antarctic. So we had to prove the power and how it would break the ice and how it would be stable. So the next video here is taken from underneath the test tank, and this is how the vessel actually breaks the ice. So the vessel doesn't go through like a knife through butter. The vessel rolls up and batters down onto the ice, and that's what breaks it. So you can see where the ice is breaking, and that goes around the bottom of the hull. So when the ship is in service, it has what's called a far sounder, and the captain and the navigator look for breaks in the first year ice, and that's where they head the ship for. So the ship will go in and roll up and break down on the ice. So we designed the ship with a Rolls-Royce. So you have to try and split the ship up into manageable blocks. So we split it up into these sections originally, and we went through a design phase of about 6 months. So from the initial design, we then split it down into 96 blocks. So the 96 blocks represents in the shipyard at Cammell, Laird, where you can see there's a huge big construction hall. Yeah, you can see from the road. Inside the construction hall, we have 4 huge cranes. So we maximise the size of the build against the crane capacity we can lift. So the biggest units that we can lift and turn is 200 tonne. So we have to design the ship around our capacity within the shipyard that allows us to put it all together. So when we've actually got a basic design, we've done the model testing, then you get what's called plan approved drawings from the Classification Society of Lloyd's Register. So they say your plans are good, they stamp them, and we can go into what's called detailed design then. So we use a 3D CAD model that you can see there now, that is what's called a propulsion train. So the 2 big grey elements there are your drive motors, so they're electrically driven, and you've got then a long pipe, that's the tail shaft that runs all the way through the bottom of the ship to the very stern end where the propellers are. So them tail shafts, they're about 42 metres long. So this is in the construction hall that I spoke about the cranes. So these are the first pieces of plate that you can see. So this was in August of 16, and this is us starting to put the unit together. So this is the very first brown little block that you've seen previously. So we built 96 of them. So altogether, from all the drawings, there's like 54,000 drawings that we ended up dealing with. And to put this ship together, there was over 1 million piece parts. So this is our first block. So that block of steel that you see there, that's about 90 tonne of steel there, and that's one of the 96 brown blocks that we showed you on the picture before. So the yellow blocks there are where we start to build it. So it's like having an Airfix kit when you're a kid. You just start to put it together. So this is the ship in quick time. So these are all the big 96 blocks going together as the ship gets built. The overall height of the ship when it was finished was 54 metres high. So this is the bow. So this was the launch. And this is the top where this is like the bridge area now that is being constructed at the same time as the lower part of the ship. So that's where we lifted. That's a 1,000-ton section with 2 crawler cranes. So this was over a 2.5-year period. So when we launched the ship, we put it into dry dock, took all the temporary structures off them. So when we were speaking before, so this is the moon pool here. So this is where they do a lot of their underwater science experiments. So have you got a small video here? So you can see the level of water in there. That's the same level of water that's outside the ship as well. So that goes right the way through the bottom. That'll be one of its ROVs, the remote operated vehicle. So hopefully that's give you some insight into how you build a ship.
But thank you everyone for coming and making great contributions. So thank you very much everyone.